Now that we've seen multiple problems and multiple proofs, I would like us to kind of distinguish between what is a formal proof and what is a justification. So for instance, in this example, it says, if m and n are integers, is the quantity 6m squared plus 34n minus 18 an even integer? Justify your answer. It does not say prove or disprove, it's just asking a quick question. So I can answer with a formal solution with the word proof and write down the steps and the details. But in this case, it's not actually asking me to prove or disprove something. It's just saying, what do you think? Is this going to be an even integer, or is this going to be an odd integer, or maybe neither? And so my answer here doesn't have to be a formal proof. This is an informal proof. I'm just going to say, yes, I think this is going to be an even integer. And I'm going to provide a short explanation why I think this is true. And I think this is true because I can factor 2 out of the numbers in the quantity that was given to me. 6, 34, and 18 can all be divided by 2, so the 2 can be factored, and that results in an integer showing up inside the parentheses, which means that 2 times an integer is going to be, by definition of even integer, an even number. So that means that 6m squared plus 34n minus 18 is actually, in fact, even. So that is basically what we call a short justification. This is not a formal proof because it doesn't have all the details of a proof. If you're not sure which one they're asking for, it's a good idea to go with a formal proof. So you can see our proofs are based on definitions and theorems, and in general, you must be able to prove the following things from definitions on a test or on a quiz or something like a homework assignment. So these are 7 statements that can be proven with the basic definitions of even and odd. So it's a good idea to practice doing some of these problems. Now, once you've proven one of these statements, it can be used to prove other examples and other theorems. This is how mathematics actually works. We're not always recreating mathematics from scratch. When we're doing math, we're relying on somebody else's work. We're taking their theorems to justify more ideas and more theorems and more properties. Now, unless I tell you to use these definitions or these properties on this slide, you're expected to do everything based on the definitions, similarly to what we did so far up until this video. Now, if you know that those statements are true, and if you're told that you can use them, then how can you go about doing that? So here's an example. It says if a is an even integer and b is an odd integer, then a squared plus b squared plus 1 divided by 2 is going to be an integer. It says prove that this is actually true. So it must be a true statement, and they want me to prove it. So that's what I'm about to do. And again, I'm going to do it based on the 7 statements that were written on this slide. So this is a formal proof, so I'm going to begin by writing the word proof at the start, and I'm going to choose the a and b, just like the theorem 1 and b2, with a being even and b being odd. And I would like to show that a squared plus b squared plus 1 divided by 2 has to be an integer. Remember, I have to use the 7 statements to prove this. I'm not going off of the definitions or the basic even odd definitions. This is very rare when I do this. I'm typically going to go off of the definitions to prove something, and you're expected to do that on quizzes and homework and tests. But I just want to show you how we can use certain previous results to get new useful results. So in this case, we know that if a is even, then the square of it is even by statement number 1. So a squared has to be even. Since b is odd, then b squared is also going to be odd by statement number 3. And notice I'm not doing the justification, I'm just referring to the statement number to provide the justification. I'm not recreating the proof myself. Now, since a squared and b squared are even and odd, then the sum of them is going to be odd by statement number 5, which means that a squared plus b squared added to 1 has to be even by statement number 2. So since a squared plus b squared plus 1 is even, then I can now use the definition of even to say that there exists some integer k that when multiplied by 2 gives me the a squared plus b squared plus 1 value. And now let's take a look at the fraction in the question. The quantity is a squared plus b squared plus 1, all divided by 2. Since the 2's can be reduced, I'm going to end up with k, but keep in mind that k is an integer. So meaning the fraction, it can be reduced, and when the fraction is reduced, I get a k that is an integer, which now proves that the quantity in question is an integer, as long as I pick a to be even and b to be odd. And that is the end of the proof.